Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here. If you've ever stared at a screen full of C++ code and just felt totally intimidated by all those random symbols, well, you are definitely not alone. Honestly, it can look like a completely foreign language at first glance. But today, we're taking our inspiration from the excellent breakdowns in Skip Uni's Lecture 13, and we're going to completely demystify C++ operators. We're going to take those abstract symbols and show you exactly how they translate everyday, real-world actions straight into efficient C++ code. By the end of this, I promise you'll see these symbols not as confusing math, but as simple, incredibly powerful tools.
To get us started, let me ask you this. How is a C++ compiler like a grocery store checkout? Now, I know that sounds like a kind of crazy comparison, right? But think about a big supermarket for a second, like a D-Mart or a Reliance Fresh. You've got items, you've got prices, things are getting scanned, and eventually you get a final bill. Well, believe it or not, the software running that entire checkout process relies on the exact same logical steps your C++ compiler uses to evaluate data. We're going to use this real-world bridge to make perfect sense of the digital world.
Okay, let's dive into this. Here is our roadmap for today. 1. The grocery store analogy. 2. Operator overloading. 3. The 6 major operator families. And 4. Precedence and associativity rules.
Starting right off with Section 1, the grocery store analogy.
Picture this. You've just been hired to design the billing software for a massive supermarket. People are throwing items on the counter, and your software needs to handle all of that data seamlessly. Let's actually walk through the checkout process step by step. Step 1. An item needs a price. When you write the code milk equals 30, that equals sign is an assignment operator. It's basically telling the system, hey, store the value 30 inside the container labeled milk. Step 2. Calculating the total. If a customer buys one item for 100 rupees and another for 50, you use a plus sign to get 150. That plus sign, that's an arithmetic operator. Step 3. The physical scanning. As the cashier scans items one by one, the system uses an increment operator, which is written as plus plus, to instantly increase the item count by 1. And hey, if the customer changes their mind and takes an item back off the counter, the system just uses a decrement operator, or minus minus, to reduce that count. So, what is the crucial takeaway here? Operators are absolutely not some deeply complex mathematical mystery. They are simply symbolic employees. They perform highly specific, entirely predictable actions on your data, exactly like a cashier performing specific actions on your groceries. All right, moving right along to Section 2, the concept of operator overloading. Now, what's really interesting about this next concept, and by the way, this comes up in technical interviews all the time, is how a single operator can wear different hats. Notice how the exact same symbols act completely differently depending on the scenario they're in. When you pair them with sin and count, these double arrows are stream input and output operators. They're helping you print text to the screen or take input from the user. But put them in a totally different context, and those exact same double arrows magically function as bitwise left shift and right shift operators, which directly manipulate binary data at the bit level. This is operator overloading in a nutshell. One symbol, multiple contexts. Think about it like a grocery store employee. During the morning shift, they might be wearing a cashier's hat, scanning items and taking payments. But during the night shift, that exact same employee wears a stocker's hat, organizing boxes in the back room. The person, or in our case the symbol, hasn't changed at all, but their function completely transforms based on the context of their environment. Next up is Section 3, the 6 major operator families. If operators are our tools, well, it really helps to organize our toolbox. Here is a clean breakdown of the 6 major operator families you're going to use every single day in C++. We start with the ones you already intuitively know: arithmetic, relational, and assignment. Then, as we dive a little deeper into the machine's actual logic, we encounter logical, bitwise, and miscellaneous operators. Let's take a closer look at what actually lives inside these families.
Let's see how this builds out practically. First up are everyday operators. Arithmetic operators are your standard math tools: addition, subtraction, multiplication, division. Oh, and the modulus operator, which is fantastic for finding remainders, like if you need to check if a number is odd or even. Next, we have relational operators. These are your comparison tools. They're checking if values are equal to, not equal to, greater than, or less than one another. Finally, we have assignment operators, like the equal sign, which we already know simply drops a specific value right into a variable container.
Okay, now we dive into the more abstract tools. Logical operators let you combine conditions. For example, A logical AND operation ensures that if condition A is true and condition B is true, then the overall result is true. Moving even deeper, bitwise operators take things down to the microscopic level. They compare binary values bit by bit. Imagine taking binary 101 and 010 and evaluating them directly against each other. Pretty cool, right? And finally, the miscellaneous or special operators. These handle very specific, unique tasks. You've got things like size of to find out exactly how much memory a data type is using, new and delete for dynamic memory allocation, and the scope resolution operator to locate specific functions. And this right here brilliantly illustrates why C++ is just such a powerhouse of language. Every programmatic need, whether it's basic addition or direct, low-level memory management, has a dedicated, highly efficient symbolic tool. You just need to know which tool to grab from your belt. Finally, we have Section 4, Precedence and Associativity Rules. So what happens when you combine a bunch of these tools into one single complex equation, like x plus y times z? How does the compiler actually know what to do first? Well, first up is precedence. You can think of precedence as the fundamental rule of priority. It dictates the very first move your compiler makes. For instance, just like the BODMAS rules you learned back in school, multiplication has a higher precedence than addition. Even more fascinating, in C++, a postfix increment, like x++, actually has a higher priority than prefix operators or standard multiplication. The compiler just consults its internal precedence table to systematically break down the equation, solving the absolute highest priority operations first. But wait, what happens when two operators have the exact same priority? Say your equation is 10 minus 20 plus 2. Addition and subtraction sit on the exact same level of precedence. That is where associativity steps in. It acts just like a referee in a tied sports match, stepping in and saying, okay, priorities are completely equal here, so we evaluate from left to right. Because of that rule, the compiler solves the 10 minus 20 first, and then it adds the 2. Now, note that a few specific operators, like prefix increments, actually evaluate right to left. But don't worry, the referee always knows the rule. To wrap up today's explainer, I want to leave you with this thought. Without these referee rules, how would your compiler ever agree on a final bill? I mean, if the grocery store software didn't know whether to calculate the tax first, or apply the discount first, or add the items first, you would literally get a different total every single time you checked out. Precedence and associativity are what bring ultimate order to the mathematical chaos. Next time you look at a complex block of code, try spotting those referees at work. Keep practicing, keep coding, and I will see you in the next explainer.